Hello, everybody. This video is a little bit of an aside from our direct talking about stars to learn about a new way, or really how astronomers go about doing their observations of stars and pretty much everything else. So this is a very practical astronomy sort of video, but yes, it is going to relate to stars, so we need to go over it. And yes, you will be responsible for this material. The subject of this video is photometry. It is a part of astronomy that is the study of how bright things are. It's the study of measuring, say, the apparent and absolute magnitude and comparing the apparent and absolute magnitudes of other stars. However, we don't just go directly at studying all of the light that we get from the stars. We have a lot of problems that come along with that, which I'll get to here in a minute. But what we do is we limit the light that's coming to us by passing it through a filter. And that's what I have displayed right here is we have a standard set of filters in astronomy, or at least in the visible part of the spectrum, or mostly in the visible part of the spectrum, that let light of only particular wavelengths in so we can limit the light that we're getting so we really know and understand the observations that we're making. There are a lot of complicating factors, and an easy way to control the complicating factors are the use of what we call photometric filters. That's what's pictured here. These are actually from an online shop. There you can buy these. I think they look really, really cool, but they are pretty expensive for a standard set that we use in astronomy. And the photometric filters are what we call UBVRI. Not as exciting until you realize ultraviolet filter, blue light filter, visible light filter, red light filter, infrared light filter. And the way that these work is they let wavelengths in. They only let a certain range of wavelengths in, and that's what we're seeing at the top here. So what we're looking at, the wavelength bar here is in a unit called angstroms. It's 10 times bigger than nanometers. So this is 300 to 900 nanometers. So ultraviolet all the way to the infrared. And what's on the y-axis here is just how much, what percentage of that wavelength of light it lets through. So nothing lets all light in perfectly. And these filters, so the ultraviolet filter only lets in ultraviolet wavelengths and lets in the most at this wavelength. And then we have blue, and this is the response curve for the blue. So how much of each blue wavelength it lets in. Then our visible filter, our red filter, and our infrared filter. And you might be thinking, why don't you just point a telescope at something and take a measurement? Well, let me go ahead and get to why we need photometric filters. Okay, this is the one that I wanted. Sorry about that. I forgot to delete the old slide. So why do we use these photometric filters? And what I have over here is just the filter name. So in astronomy, we use the standard set of UBVRI filters to do what we call photometry, which is just the science of measuring how bright something is. And if we're actually going to do that well, then we need to control the situation as well as possible. Just like any experiment that you do in science, you need to control the situation as well as possible so you can understand what it is you're observing as efficiently and as best as possible. So whenever we're studying how bright something is, whenever we're doing photometry, what we're really doing is we are going to make photometric measurements. We're going to see how bright something is. We're going to measure its magnitude because that's what we get at the telescope. And we're going to measure its magnitude through different filters. We're going to end up limiting the light. And the filters that we use, the photometric filters, the standard set, are the ones that I was mentioning before. The ultraviolet, the U filter, this is the wavelengths range that it lets in. It does not let in any light of any other wavelengths. Only 320 to 400 nanometers. You do not need to memorize these numbers. In fact, I'm going to stop reading them and you can just look. But then we have our blue filter, which is 4 to 500, our visible or V filter, as we call it, our red filter, our R filter, which goes all the way to the edge of what the human eye can see at about 750 to 800 nanometers. And then our infrared filter, which is just redder than red light, makes it through. So these are the wavelengths that pass through the filter. All other wavelengths are filtered out. They're blocked. Why do we do this? Well, one, there's no detector out there where we can observe all wavelengths at once. That kind of technology just simply doesn't exist. You can't observe all parts of the electromagnetic spectrum with a single detector. Let's take an example. Our human eye. As a detector, we only see visible light. We can't see other parts of the electromagnetic spectrum. Our retina is not equipped for it. And in fact, we're only equipped, we have blue, green, and red filters in our eye, and they have their own sort of a wavelength range. They're not these filters over here, but the only colors that our human eye can detect are a range of wavelengths around blue, a range of wavelengths around green, and a range of wavelengths around red. Our eye sees that and it measures how much blue we have versus how much red we have versus how much green we have, and it determines a color. And our brain interprets that, and that's how we actually observe and see color. One of my favorite ways to really hammer this in is if you think about the color pink. What is pink? Pink is probably best described as not green. Because if you have your blue photodetectors in your eye go off, and you have your red photodetectors in your eye go off, as in they're sensing those wavelengths of light, but they are not getting any green light, your brain interprets that color as pink. So you see pink. All right, so our eye is doing photometry. We only see a limited range of wavelengths. There's no single detector. Even the fancy technology that we build on a telescope, or like the camera that you have in your phone, which is a CMOS detector, or a CCD detector, which used to be cameras on your phone, and are still most of the detectors that we use on telescopes. They can pretty much only see visible light and infrared, a little bit of infrared, and a little bit of ultraviolet. You can make infrared photodetectors that can detect infrared, but then they can't detect visible light. So there is no single detector that can detect all wavelengths. So we already have a pretty hard situation to deal with. We can't observe all wavelengths at once, so we can't just truly measure how bright something is over all wavelengths, what we call its bolometric magnitude. You don't need to remember that term. And then even worse, within the wavelength range that detectors can detect, then it does not sense every color evenly. It might see, say, 500 nanometers really well, but 600 nanometers not well at all. So a fancy way, the proper way to say this is that the quantum efficiency is wave of a detector is wavelength dependent. That means that whenever we actually are doing our observations, whenever we're actually measuring light, it's not as simple as, hey, look, we measured light. That's why there's this entire field of photometry that studies how bright things are, which is really a study of how we measure light. So, since it's a messy situation, we need to control it. We need to use a set of filters, these photometric filters, that will only let in a certain wavelength of range of light. And then we know how that detector will sense that wavelength range of light. So if we know all those things really, really well, we can make a good photometric measurement. And that's why we're using these filters. Plus, it's just darn useful to limit the wavelengths of light. You can get a lot of information out of that. Just like with spectroscopy, looking at each individual wavelength, you can get a lot of information. By filtering the light and using photometric filters, you can get a lot of information out. So what we do when we're observing the stars is we will observe a star and a bunch of these filters, and we'll observe how bright it is in that color over that certain wavelength range. That's what we're doing in photometry. So our standard photometric filters are these over here. These are the ones that are used ubiquitously across astronomy. And if you buy a set of these filters, they are very well calibrated and they're the same the world round. So UBVRI filters are the standard. So what we're actually going to do is, let's say we look at the sun, or we look at a star that's very much like our sun. What we would do is we would say, put a blue filter and only let the 400 to 500 nanometer light in. And then we would measure the magnitude of that star, say in blue. And let's say that we measure that to be, oh, well, with only the blue light, we measure a apparent magnitude of 5.27 whenever we're only letting the blue light in. That would be what we call our B magnitude, our blue magnitude, the magnitude of that star in blue light. When you go and you look up this kind of stuff, like what is the magnitude of whatever, if you want to go use Wikipedia, it lists that for pretty much every star you can look up that has a name, and then even some that have just crazy names. Then you'll see that all of the magnitudes are visible magnitudes measured with the V filter that lets in a broad 5 to 700 most of the visible spectrum. Okay, so now that we understand that we're measuring the magnitudes in each one of these narrow wavelength ranges, what use is that? What can we use that for? Well, we can use this to define the color index, which is a really, really, really powerful tool for an astronomer because it's easy to get, as you can get it quick and fast at a telescope. And then you can translate the color index into important things like the temperature of a star. You don't need to measure its full blackbody spectrum. You can just measure it, make two quick measurements of how bright it is in two different filters, and that can give you the temperature of the star. So we define what we call the color index. So we go out, we measure how bright a star is, measuring its apparent magnitude, and each of the photometric filters. Here, I'll just list 4 of them. So we're observing a star that has a temperature of 5,800 Kelvin. That's the surface temperature of the sun. Here are the filters. So the U, B, V, and R, the ultraviolet, blue, green, or visible, and red filter. And it's just measuring how bright the star is. What's the magnitude of the star in this wavelength range? And we get numbers like in ultraviolet, it has a ultraviolet magnitude, a U magnitude of 5.91, a B magnitude of 5.27, a V magnitude of 4.77, and R magnitude of 4.5. Those are our photometric measurements. We define a color index when we take one of these, say the B magnitude, and subtract, say, the V magnitude from it. And if you're up on your logarithms, you know that since magnitudes are logarithmic, a subtraction of 2 magnitudes is really a division. So log of, say, the flux in blue divided by the flux in visible equals the log of the flux in blue minus the log of the flux in visible. You're having some nightmares about your logarithms these days, but that's just how those are the logarithmic rules. We're not going to be playing around with that. Well, really, so we're measuring flux ratios. Okay, that's a brief aside. But we have our color index, and let's take the B minus V, the most commonly used color index. Now that we have a color index, so the B minus V value for the star that we're looking at, then what we can do is we can relate that information to the fact that, oh, well, we're really sampling a blackbody curve. We're just looking at different parts of a blackbody curve, and we understand blackbody curves really well. Thank you all of that time we spent with thermal radiation laws. We know what a blackbody curve looks like. And since we know what a blackbody curve looks like, and we know that is dictated by this thing called the Planck function, you can look it up if you want to, you don't need to know it for this class. If we can just get 2 of these measurements that sample the blackbody curve, say the magnitude in blue light and the magnitude in visible light, those 2 points are good enough for us to know what the blackbody curve looks like. And if we know what the blackbody curve looks like, we know the temperature. So you can all of a sudden do something like, oh, the magnitude in B minus the magnitude of V equals some number, 0.49. Because we know blackbody curves really well, we can relate that to, oh, well, I know a B minus V value, a color index, a B minus V color index of 0.49 equals a temperature, a surface temperature of 5,800 Kelvin. So we just went to the telescope. All we did is we took 2 measurements. We used these photometric filters to measure the B magnitude of a star, the V magnitude of the star, subtracted those 2 values from each other, B minus V, to get our color index. And then that color index can tell us the temperature of the star. A new way to determine temperatures that's really, really simple and efficient. This is one of the easiest observations to make in astronomy. And all of a sudden, we can just do this, look, point a telescope at the star, have the photometric filters, measure the B minus V magnitudes, or B and V magnitudes, subtract them to get the B minus V color index, and boom, you know the temperature of the star. So I want to go ahead, since this is all a little bit new and different, I want to go ahead and spend a little bit of extra time on this. If you feel like you've got it, you can go ahead and tune on out from the video. But I encourage you to stick around, because what I'm going to do is show you the simulation where I had some of those plots from. So this is the University of Nebraska Lincoln, their blackbody and photometric filters explorer. So here I am looking at you have the curves tab, which is what I used previously. Now I'm going to the filters tab. And what it's doing is it's showing the U filter, the B filter, the V filter, and the R filter. And here's the black body curve for a temperature set by this number right here. I have it set to the example that I went through on the slides, the temperature of our sun, a star that has a surface temperature, a photospheric temperature of 5,800 Kelvin. And you would measure, if you were at the telescope, you would measure a U magnitude, a V magnitude, a B magnitude, and R magnitude equal to those values. On this Explorer, you can then set what color index you want to calculate. So here's the B minus V. I could do a U minus V or a U minus R. Each one of these will be a unique number that can be translated to a temperature. The standard is B minus V. So I just want to go ahead and take a look at this. And let's start by a very interesting temperature. So I'm just going to move this. Right here, you're seeing the relative flux. So you're seeing how, remember that bigger numbers are dimmer. So U has the smallest flux. And then BVR. I'm going to look until where we're getting about equal amount of light in each one of these filters. I wonder what temperature that is. So I'm looking where U, B, V, and R magnitudes are all equal. There we go. So 2.72, 2.72, 2.72. They're all equal. This corresponds to a star with a surface temperature of 9,670. It's better to say this corresponds to the star Vega for a multitude of reasons. One, because it's really, really bright and it's easily observable. Vega became sort of the standard star on which that's not the sun. It's the standard star in the sky that we observe at night that we started to set up this entire system around, this entire photometric system of UBVRI and these color indices. And so since Vega became our standard, there's even the Vega photometric system, slightly different than the UBVRI system. But now we have B minus V equals 0. And it doesn't matter which one, U minus V. Ooh, I'm a little bit off. Must be some rounding error in this program. But they're all essentially 0. Okay, and I want to go ahead and do this. So here we are with a B minus V of 0. So Vega is our standard star. It's also the standard for our spectral classes, which we'll be getting to in a video coming soon to you, that it is an A0 star. So if we go to lower temperature, lower than Vega, notice our B minus V values are positive. And the cooler I get, the bigger it gets, which is just saying I'm getting more visible light than I am blue light. We go the opposite direction, then B minus V gets smaller as we go to hotter. And here you can see we're getting more blue light than we are visible light. So right here, you could use this simulation. You could look at B minus V values of stars. You could tune this simulation back and forth until you get the color index that you measured. So you could actually do this with a telescope with the filters, or you could look them up. And you can crank this knob back and forth until you get the correct color index and you've determined the temperature of the star. All right, hopefully that anchors all of this. Thank you for tuning in. Photometry is a wonderful world and a wonderful part of astronomy. And yes, people spend their entire careers just being photometric astronomers. All right, I will see you in the next video.